Welcome to this tutorial on float data types in NumPy. In this video, we'll explore how NumPy handles floating point numbers, understand the differences between float16, float32, and float64, and learn how precision affects your data science and machine learning projects. Understanding these data types is crucial for optimizing memory usage and computational efficiency in your NumPy arrays. NumPy provides three main floating point data types. Float16 is a 16-bit floating point type, float32 is a 32-bit type, and float64 is a 64-bit type. The number in each name represents how many bits of memory are used to store each value. As we move from float16 to float64, we use more memory but gain more precision in our calculations. Let's compare how much memory each type uses. Float16 uses only 2 bytes per number and is called half precision. Float32 uses 4 bytes per number and is known as single precision. Float64 uses 8 bytes per number and is called double precision. This means a float64 array takes 4 times more memory than a float16 array of the same size. Choosing the right type can significantly impact your program's memory footprint, especially when working with large datasets. Creating arrays with different float types is straightforward. First, import NumPy as NP, then use the array function with the dtype parameter. For float16, set dtype equals np.float16. For float32, set dtype equals np.float32. And for float64, set dtype equals np.float64. In each example, we're creating an array with values 1.5, 2.7, and 3.9, but stored with different levels of precision. Each float type offers different precision levels. Float16 provides approximately 3 to 4 decimal digits of precision. Float32 offers about 6 to 7 decimal digits of precision. Float64 gives you approximately 15 to 16 decimal digits of precision. The precision determines how accurately your calculations will be represented. Higher precision means more accurate results, but requires more memory and can be slower to compute. Here's a practical example of precision loss. Let's take the value of pi, 3.141592653589793. When we convert this to float16, we get 3.140625, losing most decimal places. With float32, we get 3.1415927, which is closer but still not exact. Only float64 preserves the full value at 3.141592653589793. This demonstrates how choosing a lower precision type can lead to rounding errors in your calculations. Knowing when to use each type is important for optimal performance. Use float16 for deep learning models, GPU operations, and memory-constrained tasks where slight precision loss is acceptable. Float32 is ideal for general computations, graphics processing, and most machine learning applications where it balances speed and accuracy. Float64 is best for scientific computing and high-precision calculations where accuracy is critical, such as financial calculations or physics simulations. Choosing the right type depends on your specific needs for precision versus memory and speed. You can easily convert between different float types using the asType method. Start with an array in float64. To convert to lower precision, call the asType method with np.float32 or np.float16 as the argument. You can verify the conversion by checking the dtype attribute of each array. Remember that converting from higher to lower precision may result in loss of accuracy, and this conversion cannot be reversed to restore the original precision. Always consider whether the precision trade-off is acceptable for your application before converting.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.